Storing password information the correct way is an important part of achieving good security. The first rule is, do not ever store a password as plain text, because if someone has access to your password database, they'll know all the passwords. And what's worse is, users tend to reuse the same password on multiple sites. So even if you have a low-value trove of passwords because it's for some site that doesn't have much value and it's hard to steal money from, the attackers might still want the passwords not to use on your site, but in hopes that the same passwords will be used elsewhere on a bank or an e-commerce site, which turns out to be surprisingly common. But encrypting passwords does not solve the problem either. You should not store encrypted passwords either. That may seem counterintuitive, but an illustration of what can go wrong was provided when an Adobe database of passwords that had been encrypted in hints was released. What you saw was that because a block code was used, there were many passwords that had the same several characters and many hints corresponding to those same passwords. So it's possible to reverse engineer what the passwords were by correlating the hints, even though the passwords were entirely encrypted. Instead of storing encrypted passwords, you should store hashes of passwords, which don't divulge the password length and mix all the letters of a big password together so that you're not able to break it up into small chunks. Using a cryptographic hash or digest function makes it so that you have to guess the password to be able to know whether it matches the hash that's been stored. For cryptographically secure hash, that's sufficiently difficult that it's secure. However, if the user has used a predictable word, such as a common word in a dictionary, as a password, then a straightforward attack is to hash all the words in a dictionary to see if there's a match. But you don't even have to do that. You don't have to compute all the hashes because you can use what's called a rainbow table, which is a way of pre-computing hashes to make the lookup even easier. And if that sounds too hard, this has already been done for you. So if you're using a standardized unkeyed hash function, you can simply type the hex value for a hash into a search engine and find out what the password is without actually doing any computation yourself. This is why it's so important not to use a word in a dictionary as a password. Sometimes people try and be clever, such as replacing the letter O with a 0, but a strong dictionary attack will also know those common substitutions and can still use a rainbow table to be able to determine the hash very quickly. Assuming you've used a password that is not a straightforward dictionary word or adaptation of a dictionary word, then you can further improve strength by using salt and pepper. Salt is random extra text, and pepper is systematic extra text. Well, how can random extra text work here? The idea is that, for example, if you have a salt of a single numeric digit 0 through 9, then when someone types in a password, you add a digit 0 and see if there's a hash match. If that doesn't work, you try 1. If that doesn't work, you try 9. What you've done is that you've made it 10 times more expensive for an attacker to check the hashes. While it's 10 times more expensive for you, you know that you only have to try 10. But the attacker has to compute all the words in their attack dictionary, and that's multiplied by 10, leading to a significantly increased either computational burden or size of the rainbow table. Salt doesn't solve all problems, but it's always nice to make the attacker work harder. Pepper is systematic extra text. You might add 20 characters that are always the same every time you check a password, and the attacker would have to know those 20 characters to be able to compute an effective hash function. Now in an embedded system, they might reverse engineer one of your units and figure out those extra 20 characters. So you cannot pin all of security on salt and pepper, but in both cases they're making it a little bit harder to attack, which is usually a good thing. There's an additional technique generically called key stretching. The idea for key stretching is to take the password and perform some transform on it to mix the bits a little bit, to make it a little bit longer, to basically try and get more bits worth of password out of a fixed value. There's a standardized algorithm called PBKDF2, which does key stretching. And the idea here is just to have the attacker have to deal with a larger value than just whatever password the user types in. Ultimately, salt, pepper, key stretching are just tricks to make it a little more expensive to attack. In the final analysis, if your users are using weak passwords that are easily guessable, they're going to be easy to attack, but these are best practices to help increase the cost of attacks and therefore decrease somewhat the probability of a successful attack.